So this will be the derivation of the beginning of the derivation of the Navier-Stokes equation. And basically the way to set this up is basically to use simply essentially force equals mass times acceleration. So basically the assumption is there's some fluid, which I'm going to draw here. So I assume we have some volume of fluid. And of course there's flow through the fluid. So it's doing something, it's flowing. So the idea is to basically figure out how to go ahead and compute how this fluid flows. So instead of trying to calculate how the entire fluid moves, the concept is to break the fluid down into these little cells. So basically subdivide the fluid to all these little cells. And then by subdividing the fluid into these little cells, I instead look at the velocity in each of these little tiny cells where that fluid is actually going. So each of these cells may have a different velocity. So another way to see this is with the program. So basically what's going on here is this is actually the output from the program. This is basically a map of these velocities. So what's happened is this fluid space has been divided into a grid, and each cell in this grid basically has a velocity attached. And as time progresses, these velocities change to indicate how the fluid dynamics are changing, or how the velocities in the fluid are changing with time. So the idea of the Navier-Stokes equation is actually to take a little cell that's kind of like a volume around a particle, and then just follow where that particle goes with time. For instance, if you take something in the middle of, off to the side of this thing, wait till it restarts, and it starts kind of off at the side, it kind of goes around in this vortex and moves off to the side, as far as it's moving with space. So basically, go ahead and take one of these guys and call it K. And when we take a little volume around it, so we take basically some kind of fluid blob volume. Let's say, didn't draw that very well. Here's the little volume. Kind of a blob, and this is moving around the kth particle, whatever that means. So that's basically that guy. And this will be called WK. And now since the particle is moving with time, this volume is actually time dependent, as the volume will basically move across in space, which means it'll move across the velocity field, and it also might expand or contract or morph somehow, because as the velocity changes, it might get thinner or fatter as it moves in space. So this is basically considered this kind of fluid blob that's surrounding the particle K. So The idea of the Navier-Stokes equation is to do force equals mass times acceleration. So we basically want to look at what are the forces that affect this little fluid volume. So to begin with, have the fluid volume. First force that's going to affect it is pressure. So pressure comes in from the sides. So this is just the normal pressure that's exerted from all the other parts of the fluid. Pressure. So if one side is greater though than another side, then there's going to be a net pressure if there's a pressure imbalance. Force So that's one force. The next force, which is specific to the Navier-Stokes equation, is viscosity. So basically, here's a fluid again. The blob's doing whatever it's doing. But the fluid might be flowing faster along the top maybe than it is along the bottom. So viscosity essentially is an attraction force between fluid. So what viscosity causes is when one part of the fluid moves faster than the other part of the fluid, it actually basically causes a force. That's like a drag force. So viscosity basically causes force. Two differences. Velocity. You could call it layers. That's called fluid layers. Though that's not probably the most perfect term, but it's basically caused by a difference in velocity. Essentially, it's like velocity. Basically like a drag force. I'm going to go back and erase that because that is a mess. So that goes down to viscosity, and then there's one more force. And this is actually extremely simple. So the last force to look at is just the net force that's not position dependent. So if there's a force, fluid blob, and say that it's under the influence of a force like gravity, there's just a net force that's proportional to basically the total mass of the blob. So this is basically called the external force. So force is basically all pressure. I'll write this in. Viscosity. Can cause force. And any external force such as gravity. So to start with, instead of solving the Navier Stokes, I'm going to just go over the Euler equation, so which basically means I'm going to ignore the viscosity for the moment. And then I'll put it back in later, but viscosity has some peculiarities that need to be addressed, so it's easier to just go through the Euler first. Okay. So the Euler equation is what just did, as far as this is, just to reiterate, this is basically comes from d by dt, mass times velocity equals force. And then we're basically going to do this law in terms of the fluid blob. So in terms of the blob W, it turns actually into an integral equation. So this is basically integrating over the W around the kth particle at a given time. And then rho, which is the fluid density, that essentially is the mass. U is the velocity of the fluid. That depends on its grid location as well as its location in space and time. And then the volume interval dx dy dz volume. So this is basically mass times velocity, and this is the d by dt. And then this equals another volume integral same blob, of course, integrating over the net force, which depends on location and time. And then, of course, the same integral. So, to go over this in a little bit more detail, where this actually comes from. So basically, take the W, which is actually the blob, that came out of the subdivision into these little cell blobs, and actually divide this blob up even more. So another subdivision, this time on the blob itself. So this is the blob. Blob. And so each of these cells inside of each of these guys have a little mass, whatever was in there, and then the velocity, which we're going to do u, whatever was there, and then the force vector on whatever was there. So of course U sub is actually dependent on space and time, and force sub is also dependent on space and time. And then the mass sub is where the density field comes in. So the mass sub is actually going to be essentially the density at that location. That can depend on space and time, and then times the little volume of that location. So what is basically done with this is to again apply force equals mass times acceleration. So what happens is force equals mass times acceleration basically means sub with d by dt, turning that into acceleration. So this is mass times acceleration equals the force on that sublocation. So this would basically be changing with respect to time. This time the rho, which is the density at that location in space and time. And then I'm going to weave these things to the end. So then you have the u, which is the velocity, again space and time, delta x, delta y, delta z, and this equals force of the sub. Basically this force is actually need to go ahead and change my notation slightly here, because this is actually going to be the capital F force. Which means the total force on the sub, which of course will also depend on space and time. However, the total force on the sub actually goes like a volume dependent force. So this is basically force per unit volume of the sub times the volume. So you could, in the sense of gravity, obviously the gravity depends on how much mass is there, so there's basically a volume dependence. As water, it turns out water density is pretty much fixed, but depending upon how much volume is getting multiplied by basically a constant, that depends how much force, the net force that's actually being exerted on that little block. So what this basically turns into maybe I'll put the room. I'll put the x, the t in there. So basically what happens in the end is you basically sum over all of those little blocks inside the volume. So this is a sum over all of these little squares. And summing over all these little squares times this equation basically will get the total balance for, will basically apply Newton's laws to this volume W. So for each of these little squares in the volume, this equation basically holds. So writing this out again, that's the density for each of those little subsquares times the velocity in each of those subsquares. And then there's the volume term. And this equals likewise the sum over these individual volume-dependent forces that also depend on space and time, and then the volumes. And this is summed over all the subdivision. So that's how that, and that's basically the total for basically force balance equation for the entire little block there for all of W. So all subs in T. However, these sums can basically be converted into an integral. And so this is basically just a volume integral. So going from the discrete case to the continuous case, the sum becomes the integral the d by dt can be moved out of the sum. And then you basically just have the row. The velocity. And then dx, dy, dz equals, again, the triple integral ends in t. The net forces, then all the volume dependent force per unit volume net, which will be gone into in more detail later. Right now, the first thing that will be solved is the left side of the equation, and then the right side will be gone into in more detail later on. So for right now, it's just going to be listed as force net instead of breaking it down into pressure and gravity and viscosity and the rest. And then of course the integrals. So that's equation that is basically at the top. That's where it comes from. So this equation basically comes from subdividing this and then applying force equals mass times acceleration for each one of these little units. And I just realized that notation error, because I'm actually not using that for this this is what I'm using for the net force. Okay. So basically, the next step is to solve the time derivative on this side of the equation, which would be trivial, except that it turns out since the volume depends on time, it's actually a bit more complicated. So this type of time derivative, in a general sense, unfortunately there's not enough letters, so I'm going to rewrite this again, but the general problem for this guy is solving an equation of the form which is basically d by dt, a volume integral over some volume that's time dependent, and then has an f. This is not the force f, this is just the generic f for function f. And this function depends on space and time. And this is the volume. And the question is what this goes to. So basically the trouble is because what happens with W is basically W will deform. So there's basically this velocity field which actually I'm going to pull up the other side, see this more easily. So there's basically this velocity field, but as W moves over this velocity, basically the velocity inside the blob is actually changing. So if W is moved from here to here, the velocity is changing both in direction and it's also changing in magnitude fairly considerably. So the problem with the W being time dependent is that the X, which is the X is basically fixed in space. So this function basically is a fixed function that depends on space and time. And this velocity, is basically going to be moving over that equation. So if I basically draw my velocity field, so the velocity field basically changes in direction, and then I start out with my blob here, and then I basically take this thing and I basically move it to another location. What's happened is my velocity has now changed because the blob has basically moved. And this is basically t. So the problem with doing this integration is I can't just move this in and integrate the velocity field. I'm actually going to call this U. So we use it for velocity field. I can't just go ahead and integrate the velocity field, because if I just integrate the velocity field, what that would be doing is that would be just looking at the static velocity field. So say I have a velocity field that looks like this at t. And then if what might happen is, let's suppose at t cradle time, let's say it goes and increases or something. So what will happen is if I just move the d by dt in and integrate the u, what will happen is I'll basically be doing this. So it'll be just accounting for changes in the actual velocity field. But it also has to take into account changes in the motion of the w. So the way to actually do this is something called the Leibniz rule. See if I pronounce that correctly. So solution is the Leibniz rule. And that will basically be the topic for the next optional section. After I solve that, this will start up again using the Leibniz to solve the left-hand side of this equation. So as to solve that. And then it will go back to the derivation of the Euler